Hello and welcome back to our fourth trigonometry lesson. We are going to use sine and cosine ratios to find some unknown side lengths. So first thing, we want to go back and recall our acronym, SOHCAHTOA, right, with SO, meaning that when I'm looking at the sine ratio, right, the sine of an angle, it's comparing the opposite to the hypotenuse sides. Right? And when I look at, I need to color code this, when I look at the cosine ratio, so, right, talking about the cosine ratio, that's going to compare the adjacent sides to the hypotenuse. And when I look at the tangent ratio, going way back to our first video, we're looking at how tangent, the TOA portion, how that compares the opposite side length to the adjacent side length, with opposite in the numerator, adjacent in the denominator. Right? So with all three of these ratios, we can successfully compare any two of the three side lengths, given a specific reference angle A, right? Telling us how those two sides compare. So when we're finding side lengths, right, when we're finding either the opposite or the adjacent or the hypotenuse one at a time, we must have a known angle, right? We have to know an angle, or else we'll have too many unknowns. And then we have to know a side length, and what side length we do know helps us determine which ratio we're going to use. So if we have an angle and one of the opposite or hypotenuse, we want to use sine, right? Again, because those are the two lengths that sine relates. If I have, right, hypotenuse or opposite, that's going to tell me use sine. If I have the adjacent or the hypotenuse, right, and I'm trying to find one or the other, right, if I have my adjacent or I have my hypotenuse, then I'm going to use the cosine ratio. Right, same as before, it's super important that we always label our sides based off of a reference angle, so we know what formula we're using and why. So let's look at some examples. Let's find the length of BC, right? So finding the length of this side from point B to point C. We have an angle given to us already, so let's assume that's our reference angle. Let's label our sides based on that 50-degree angle. The side length that's opposite is length AB or BA. The side length that's adjacent is BC or CB. Right, and the hypotenuse is this 5.2 from A to C, right, because it's opposite that right angle. So we want to find length BC. This is where we kind of do some inventory. We say, all right, I have an angle. What else do I have, right? Well, I have the hypotenuse. So looking at SOHCAHTOA, right, we always want to use the information we have. I'm not going to be using tangent here because that wouldn't use this value I know. It wouldn't use this 5.2. And I'm trying to find the adjacent. Right, well, the adjacent needs to show up in my ratio for me to solve for it. So that tells me I'm going to be using cosine. Right? Sine would require me to know the opposite length. And same with tangent. Right? So cosine is what we're going to go with. So I write out my formula. Always start with a nice blank slate. Cosine of an angle, right, is adjacent over hypotenuse. Pulling that right out of my acronym. Now I'm going to fill in the blanks. This time I know the angle, so I'm going to replace that theta with a 50. I don't know my adjacent side. We can leave it as an A. We can call it X, right? We could do whatever. It's our unknown. But I do know my hypotenuse. I know that it's 5.2. And so we've done this before, right? It's solving our proportions. I'm going to cross multiply, right? Or multiply both sides by 5.2 so that it disappears from the right side, right? The right side has gotten 5.2 times bigger, so now it's just X. But the left side had to get 5.2 times bigger, so now it's 5.2 cosine 50s. Now, this is where the calculator comes in, same as always. I have 5.2 was my hypotenuse multiplied by that cosine ratio, right? That's going to leave me with the adjacent cosine of our angle, which was 50 degrees. And it tells us that that side length is 3.3. So x equals 3.3, or you could say BC is 3.3 centimeters. All right, but using the angle, knowing that cosine of 50 has a specific ratio, right? If we even looked at our calculator, just the cosine of 50, the ratio is 0.6428, which seems like gibberish, but it's telling us that the adjacent side is 0.643 blah 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 times the hypotenuse. All right, so knowing how those sides relate with a 50-degree angle can help us find one of the unknown sides. Let's try another one. Find the length of AB. So here is what we're finding. All right, let's call that x right off the bat. We're using the same triangle where we have the same angle. We're going to label the sides. They're going to be the same. Right? This time our unknown is the opposite. The adjacent is still over here. This is still our hypotenuse because the same triangle, the same reference angle. We're just looking for a different unknown. This time, right, we want the opposite. We have the hypotenuse. And so we're going to use the sine ratio. We're going to use the SO part of SOHCAHTOA. So again, start with a nice blank slate. Sine theta is, and then we pull it out of our ratio, O on top, H on the bottom. Plugging in the values we have. The sine of angle 50. O on top, again, that's going to be x. That's our unknown. That's what we're trying to find. That is length AB is the opposite of this angle. But we know that the hypotenuse is 5.2. Right, so let's look. If I pull up my calculator, sine of 50 gives me a different answer, right? Because it's comparing a different side to the hypotenuse, right? We know that when I'm talking about the sine of 50, I'm talking about the opposite length, right? I'm talking about how big of an angle is created. Whereas when I'm talking about the cosine of 50, I'm talking about the adjacent. I'm talking about how long the two arms on either side of the angle are in comparison. Right, so the size of the angle changes the ratio, and depending on what ratio we're looking at, it's going to be different because we're comparing different sides. So I cross multiply, I multiply by 5.2. The process is exactly the same. Right, because I'm solving for the unknown, and that unknown happened to be in the numerator. But I'm just using a sine ratio this time instead. So I'm now doing 5.2 times sine 50. And that tells me 3.98, right? Rounding that up, that gives us 4.0. So length AB of this same triangle is 4.0. Right? But hey, if we had realized a little earlier that this is the same triangle, and we already said that this was 3.3, we could have done a lot of different things. I could have used just Pythagoras to figure out length AB because I know two of my three sides. I didn't have to use trigonometric ratios because I'd already done some of the work, right? Or if I had the adjacent side, I could have used the tangent ratio, right? I wanted to know the opposite, and I technically have the adjacent from the work I did in example 1. If at all possible, we prefer to use the numbers given in the equation, right? Because if we're going to use numbers we've already found and we made a mistake in the first part, that mistake's going to follow us into the second. Okay? So let's do a couple more. Take a minute, pause. I want you to give these a try. See if you can choose the right ratio and solve for that side length, that unknown side length. So find the length of DE. And if I label my sides, it looks like this is opposite, adjacent, and hypotenuse. So going through this again, always remembering that acronym, SOHCAHTOA. right? First of all, I'm trying to find the hypotenuse. That's my unknown. So we want to make sure, right, we're using something involving the hypotenuse, so that cancels out tangent. And we know the opposite, right? We want to use the information we're given, so we're going to use sine for this one. Sine of 55 degrees. Now let's start with a blank copy sine theta, just so we're super sure we have the right ratio and we've set up the formula right. Showing all of our steps. Input that 55-degree reference angle we're using. And that 55 degrees is opposite the 6.8 with x as our hypotenuse, right? If we remember cross multiply and divide, this is where we have to do a little bit more work because that variable is currently in the denominator. So I now have x times sine 55, right? I made both sides x times bigger, which pulled it away from the right side. I then have to divide both sides by sine 55. Right? Because I'm trying to isolate x. So this time I have my opposite side divided by my ratio. On my calculator, I put my opposite side first, divided by my sine ratio. And if you're not using a fancy internet calculator like me, I'd recommend putting brackets before your sine so that it knows this whole thing is in the denominator. Our angle was 55 degrees, yeah. And we get a length of 8.3. So 8.3, look at our units. Looks like it's centimeters. Number 4, hopefully you've given this one a try. Determine the value of, the length of JK. Right, labeling our sides given this reference angle of 65 degrees. We have our opposite, our hypotenuse, and our adjacent. Right, I want to find the hypotenuse. This time I know the opposite. So we're going to use sine again here. Right, sine theta, because we have the opposite, we want the hypotenuse, so this is the only ratio involving both. Plug in my values, my angle of 65 degrees gives me a 7.6 as my numerator, and an x, right, our unknown, our length jk on the bottom. Cross multiply, but that's not our last step. We have x times sine 65. I just tend to write the x out front. You could also write 65, sine 65 times x equals 7.6. Then we divide out that whole sine of 65, right? I can't pull out just the 65 because it's not actually by itself. It's not a coefficient, right? It's not being multiplied by anything. It's stuck inside that sign, right? These two things move as a unit. That number is not a traditional number we're used to. Right? It's part of the sine function. Just like you can't pull something out from inside a square root. So x is 7.6 over sine 65, which when we plug that in here, 7.6, oops, there we go, 7.6 divided by sine, looking at my angles again, 65. And I get 8.4, it looks like. And centimeters are our units. Right, so using those angles, using what we have and what we know to help us decide which of the 3 ratios we're going to use. So let's try a couple of application problems. How far is it from the transit to the survey pole? So we are looking for this length here. Right? Again, we can't measure that in real life because there's a pond in the middle. Right? Unless you have some way to get your measuring tape across the pond, it can be easier to measure the distance from one place to the next, right? And from another place to the next, and use the idea of a right-angled triangle. So we are looking for, if I label this, looks like my hypotenuse. they've given us this angle down here of 46.5. So in comparison, our opposite would be across the pond, and our adjacent would be from the survey stake to the transit. So this time, we want the hypotenuse, right? That's our unknown. We have the adjacent. So thinking again, always SOHCAHTOA. Again, it's never going to leave your brain. SOHCAHTOA, A and H, right, is the two we're working with. So we see cosine is going to be our best bet here. Again, start with a blank slate. Cosine is adjacent over hypotenuse. Plug in the things we know. We know that angle is 46.5. We know the adjacent side is 110 meters. We don't know the hypotenuse. So same thing we did in the last two examples, right? The only difference here is we have a picture with some context. Cross multiply first. I want that that variable to show up in my numerator instead. I have x, oops, wrong color. I have x times cosine 46.5, and I just am left with 110 on the right side. I divide everything by cosine of 46.5. Right, that inverse function is only showing up when our angle is unknown, but we have our angle this time, so make sure you're just using that plain old cosine button. All right, we just want to make sure numerator goes first. 110 divided by cosine 46.5. And we get a length across the pond of 160. So we can say 160 meters from the transit to the survey pole. All right, and a value that would not necessarily be able to be measured because of that pond in the middle. Another example, how far is the plane from the radar station? So we see, right, it says required distance here. When we talk about the distance from the plane to something, we're assuming along the plane's path of travel, right, the straight diagonal line. We have an angle here. We'll label our sides as per usual. Our opposite is across the way. Our hypotenuse is what we're trying to get. Our adjacent, we know the distance along the ground, right, the horizontal distance from the radar station to the plane. And so we see again, we're going to be using cosine, right? We have adjacent, we need hypotenuse. You might say to yourself, I'm going to use cosine again. So cosine theta, we're going to get really good at writing these ratios out here soon. Our angle this time was 32.5. And that's equal to, in terms of the ratio, an adjacent length of 35.6 compared to our unknown hypotenuse. Cross multiply and divide, right? Bring that x to the other side. X equals 35.6 over cosine 32.5, because we know this is where we're going to end up. We've done it about 3 or 4 or 7 or 8 times at this point. 35.6. Oops, lost the 6. Let's try that again. 35.6 divided by cosine of, I already forgot my angle, 32.5. And we get 42.2. So the plane is 42.2 meters from the station. And it's always worth a minute to take a minute and critically think about this, right? Is your hypotenuse the longest side? Well, yeah, it's at least longer than the adjacent side we were working with. So that makes sense, right? Does it seem like a reasonable number? Yeah, right, they're pretty fairly close together. If it was somehow telling you now that you were 4,000 meters away, that might be a little bit off, right? Unless you were dealing with a tiny, tiny, tiny angle or a huge, huge, huge angle. Okay, so take a minute, critically think, say, does my answer make sense? Yeah, it probably does. So that's where we're going to finish this lesson. We've basically done the bulk of trigonometry at this point. All right, we've covered all three ratios. We're now going to, in our next lesson, look at solving triangles. So how can we find every single unknown portion, right? All the angles, all the sides, deciding when to use sine, when to use cosine, and when to use tangent. So if you have any questions on this video, feel free to send me an email, drop by your tutorials or focus. Be sure to hit that